Our cities are dense with people. Millions walk through train stations, plazas, and shopping malls every single day. Each step they take contains a small amount of kinetic energy. When a foot hits the pavement, that energy is normally lost. It disappears into the ground as tiny vibrations and a little bit of heat. A new generation of technology is changing this simple fact. We can now build floors that capture this wasted motion. These smart floors turn the pressure of human footsteps into usable electrical power. They are creating a new type of power plant, hidden in plain sight, right beneath our feet. This concept is often called the urban battery. It is not a single battery in the traditional sense. Instead, it is a distributed network of power generation and storage. Every tile in a busy walkway becomes a tiny generator. When thousands of people walk across them, the small amounts of power add up. The entire floor acts like a battery for the local area, charging itself with every person who passes. This matters because it provides a source of clean, hyper-local energy, reducing reliance on the central grid and making our urban spaces more resilient and self-sufficient. The core idea is simple. A person walks, a tile moves down by a few millimeters. This small vertical movement drives a tiny generator inside the tile. The generator creates a pulse of electricity. This process is based on a proven principle called electromagnetic induction, the same principle used in large-scale power plants. The technology has now been miniaturized, fortified, and made reliable enough for the world's busiest public spaces. This is not a futuristic dream. It is a practical solution being deployed in smart cities today, in the year 2026, to power our increasingly connected urban lives. Why is this technology so important now? Our cities are facing an energy challenge. We need more power, but we have less space. Rooftops are great for solar panels, but sunlight cannot reach the deep urban canyons or underground subway systems where millions of people move. Wind turbines are not practical in the turbulent, tight spaces between skyscrapers. Footsteps, however, are a constant and predictable energy source in these exact locations. Kinetic floors offer a way to generate power in places other renewables cannot. This local power source can keep essential services like lighting, communication nodes, and safety systems running, even during a wider grid outage. The energy in a single footstep might seem small, but the scale of human movement in a city is immense. Consider the sheer volume of people. Each day, hundreds of thousands, and in some cases millions, walk through the same corridors and plazas. Every one of those steps represents a packet of mechanical energy that is currently being wasted. By understanding the numbers, we can see the true potential of this untapped resource. The energy is not in one powerful event, but in the relentless, cumulative effect of countless small movements. This is the power of the crowd, turned into literal electrical power for the city to use. Let's look at real-world examples to understand the scale. Times Square in New York City is one of the world's most famous pedestrian zones. On an average day, it sees between 220,000 and 330,000 people. London Bridge Station, a critical transport hub, can have over 500,000 passengers passing through its gates during peak travel times. The undisputed champion of foot traffic is Shinjuku Station in Tokyo, which serves over 3 million people every single day. These are not just numbers. They represent a massive flowing river of kinetic energy that passes through these locations hour after hour without fail. A single human step contains a surprising amount of energy. Scientific studies estimate that the total mechanical energy in an average walking step is between 300 and 510 joules. Of course, we cannot capture all of that, but the latest kinetic tiles of 2026 are efficient enough to make a real difference. A modern electromagnetic induction tile can reliably harvest about 5 joules of electrical energy from a single footstep. In a busy transit concourse where 50,000 people each take just 500 steps across a harvesting zone, the system can generate tens of kilowatt hours of electricity over a few hours. This level of generation is significant for local needs. It is more than enough to power the area's LED lighting around the clock. It can run a network of small 6G wireless cells, improving connectivity for everyone in the area. It can keep digital information displays and emergency signage operating continuously. The key is density. The system works best where people are concentrated. By strategically placing these tiles in the choke points of our cities, station entrances, ticket barriers, and popular plazas, we can turn these zones of congestion into zones of clean energy production. The technology that converts a footstep into power is elegant and robust. Modern systems rely on electromagnetic induction, a principle far more effective and durable than older piezoelectric methods. When a person steps on an EMI tile, the surface plate depresses slightly. This small vertical motion is the input. Inside the tile, a clever mechanism translates this linear push into high-speed rotation. A central lead screw, a threaded rod, is the key component. As the tile moves down, a nut connected to the surface travels along the screw, causing the screw to spin rapidly. That rotation is harnessed by a small generator. The lead screw links through a set of bevel gears, which connect to a miniature DC generator. The gears are tuned to multiply speed, ensuring the generator spins fast enough to produce a useful current pulse from a brief footstep. The whole assembly is engineered to be incredibly durable. It must withstand millions of compression cycles without failing. The result? The downward force of a person's weight becomes a pulse of direct current, ready to be used or stored. Why is EMI superior to piezoelectricity? Piezoelectric materials generate a small charge when squeezed, but they have big drawbacks. They are brittle and can crack under heavy foot traffic, and they produce very little power per step, useful only for novelties. EMI systems are mechanical, built from steel and durable polymers, designed for public spaces and producing significantly more power per step. Key numbers for a 2026 EMI tile: stroke typically 5 to 10 millimeters, barely noticeable while walking. Lead screw often has a steep 45-degree lead angle, which generates lots of rotation from a short stroke. Generator electromechanical efficiency is around 26%. With smart power management, overall efficiency is higher. Many tiles are rated for over 20 million cycles before major maintenance. The electricity generated by kinetic tiles is direct current and comes in short, powerful bursts. This makes it ideally suited for powering local, low-wattage devices right where the energy is produced. Hyperlocal generation avoids transmission losses. The power is made on the spot and used on the spot. Adaptive LED lighting is one obvious application. A single footstep can power a bright LED for tens of seconds. In busy places like subway corridors, the lights can run continuously from footsteps alone. Interactive lighting can brighten along a person's path as they walk, creating a safer, more engaging environment while using energy efficiently. This power also fits 6G microcells, small wireless nodes for dense connectivity. They need a distributed low-power network. Kinetic tiles can provide that steady trickle. Another critical application is emergency systems. During a grid outage, the central power goes down, but a floor powered by footsteps keeps generating electricity as people move. That can keep essential emergency lighting operational. That can keep exit signs lit. That can power digital wayfinding displays. In a crisis, that resilience can be life-saving and guide people calmly to safety. The same power can support the growing IoT network that makes a city smart. Small environmental sensors, air quality monitors, public information tickers. Running wires to every sensor is expensive and complex. Kinetic tiles offer a wire-free solution, providing the energy needed to run these on-site edge computing devices. That lets cities deploy denser, more responsive sensor networks without loading the grid. Modern kinetic tiles do more than just generate electricity. Each tile is also a sensor. Embedded within the unit is a small, ultra-low power microchip. This chip uses a tiny fraction of the generated energy to analyze the footstep that created it. It measures the precise timing of the step. It measures the amount of pressure applied. Networked together, the floor becomes a massive real-time data collection platform. It creates a live heat map of crowd density and movement, showing where people are congregating, showing which paths people take. This data layer has huge practical value for managing public spaces. Facility managers use these crowd maps to optimize building systems. The system can detect a surge of people entering a station and signal HVAC to increase airflow before it gets hot, improving comfort-saving energy. In an emergency, the system can change floor lighting, change digital signs, guide people away from congested areas, guide them toward the clearest, safest exits. The floor becomes an active participant in building management and public safety. The kinetic floor provides unmatched accuracy and granularity. Use this data to inform store placement, optimize advertising, improve customer experience. Revenue from selling anonymized data can be a key part of ROI. Data collection must be handled with care to protect privacy. The system is privacy-preserving from the ground up. Raw data from a single footstep is processed at the edge on the tile. The chip converts pressure and timing into an anonymous data point. One person stepped here at this time. That anonymized info is sent to the central server. Sensitive biometric details never leave the tile. Individual privacy is protected. Crowd-level analytics are still maintained. Storing the surge. Hybrid systems for erratic energy. The energy from footsteps is not a smooth, continuous flow. It arrives in short, intense bursts, one step at a time. Furthermore, foot traffic itself is not constant. It peaks during morning commutes and evening commutes and drops off significantly overnight. To make this erratic energy source useful, a smart storage system is essential. The most effective solution, widely adopted by 2026, is a hybrid approach that combines two different storage technologies: supercapacitors, lithium iron phosphate batteries. Each technology plays a specific and complementary role in stabilizing the power supply. Supercapacitors are the first line of defense. They are brilliant at handling the immediate sharp spikes of energy produced by a single footstep. A supercapacitor can charge and discharge almost instantly, hundreds of thousands of times, even millions of times, without degrading. When a person steps on a tile, the burst of DC electricity is sent directly to a local supercapacitor. This component absorbs the energy pulse and smooths it out, providing a stable, clean voltage that is safe for sensitive electronics like LED drivers, wireless transmitters. They act as a buffer, protecting the system from the chaotic nature of the input power. While supercapacitors handle the short-term fluctuations, LiFePO4 batteries are used for long-term energy storage. Throughout the day, when foot traffic is high, the tiles will often generate more power than is needed at that moment. This excess energy, once smoothed by the supercapacitors, is used to slowly charge a centralized bank of LiFePO4 batteries. This stored energy can then be used later, during periods of low foot traffic or at night, to keep lights and other systems running. This ensures a continuous and reliable power supply 24/7, even though the energy is only generated during busy periods. The choice of LiFePO4 chemistry for the batteries is a deliberate one, focused on safety and longevity in a public infrastructure context. Unlike older lithium-ion chemistries, nickel, manganese, cobalt, LiFePO4 is much more chemically stable. It is far less prone to thermal runaway and fire, making it a safer choice for installation in crowded public spaces like subway stations, airports. LiFePO4 batteries also offer a longer cycle life, meaning they can be charged and discharged more times before they need to be replaced, which lowers the long-term operational cost of the entire system. The economics of walking: costs, payback, and new revenue. The financial viability of kinetic energy floors has improved dramatically in recent years. As the technology has matured and manufacturing has scaled up, costs have fallen. As of 2026, the capital expenditure (CAPEX) for installing these systems in a new building project is approximately £80 per square foot. For a significant installation, such as a 5,000 square foot airport concourse, the total initial cost would be around £400,000. While this is a substantial investment, the operating expenditure (OPEX) is very low, and the system opens up multiple streams of revenue and savings that lead to a surprisingly quick payback period. The primary financial benefit is direct energy savings. By generating electricity on site, the building avoids the cost of purchasing that power from the utility grid. In areas with high electricity prices, this can add up to significant savings each year. The system also helps to reduce peak demand charges, which utilities often levy on commercial buildings for their highest period of energy use. Because the tiles generate the most power during the busiest times of day, they naturally help to offset this peak demand. In many regions, the clean energy generated also qualifies for renewable energy credits, RECs, which can be sold for additional revenue. A second and increasingly important revenue stream comes from the data layer. The anonymized footfall data generated by the floor is extremely valuable to retailers, advertisers, building operators. This data can be licensed to provide insights into consumer behavior, crowd flow, and space utilization. In high-value retail locations like flagship stores or major airports, the revenue from data licensing can sometimes equal or even exceed the value of the electricity being generated. This transforms the floor from a simple utility into a powerful business intelligence tool, fundamentally changing the economic calculation for the investment. When all these factors are combined, energy cost avoidance, REC sales, data revenue, and predictive maintenance savings, the return on investment becomes very attractive. In the most ideal locations with extremely high and consistent foot traffic, the payback period can be as short as 3 to 5 years. For less dense areas, it may be longer. The key is careful site selection. The economic model works best in the world's transportation hubs, major tourist attractions, and flagship retail centers. For city planners and building developers, the decision is becoming less about if and more about where to deploy this technology for the best financial and environmental return, keeping the system alive, maintenance, safety, and standards. For any piece of public infrastructure, reliability and safety are paramount. Designed with that in mind, smart tech minimizes maintenance and enforces strict safety standards. The old model of scheduled preventative maintenance is inefficient. Modern tiles use predictive maintenance. Each tile has internal sensors monitoring its own health. Sensors track vibrations. Sensors track temperature. Sensors track electrical output. Embedded low-power NB IoT radios report status to a central hub. A maintenance worker uses a tablet that shows a floor plan with a single red tile. Self-reporting is a game-changer for operational efficiency. The tiles use the industry-standard MQTT messaging protocol. They send small packets over the cellular network. If sensors detect abnormal vibration that might indicate bearing wear, or a drop in power output that suggests a generator issue, the tile automatically sends an alert. Crews are dispatched only when and where needed, with specific problem data. This eliminates unnecessary inspections, reduces labor costs, maximizes system uptime. The floor is almost always generating power. Safety and user comfort are governed by rigorous international standards. ISO 2631 covers whole body vibration exposure. The tile's maximum displacement is typically capped at 10 millimeters to ensure the surface feels stable and secure underfoot. Feels like a high-quality athletic floor, or a sprung dance floor. Edges are tapered and beveled to prevent trip hazards. Engineers run modal analysis to avoid harmonic vibrations affecting the building. Electrical safety is critical. Fire safety is critical. Systems use low-voltage DC to reduce electrical risk. All wiring and components are sealed and waterproofed to protect against spills and cleaning fluids. The materials used in the tiles are selected to meet strict fire safety codes for public assembly spaces. Designed to comply with safety and building standards, cities can deploy with confidence. Safe, comfortable, reliable. The ethics of our gate. Privacy and ownership in the kinetic city. The ability of kinetic floors to sense footsteps in high detail introduces important ethical questions, primarily privacy. Every person has a unique way of walking, known as their gait signature. This signature is a combination of timing, pressure, rhythm. In raw form, this data is a biometric identifier, fingerprint facial scan. If captured and stored, it could be used to track people across a city. That creates a major privacy risk. To address this, legal and technical frameworks exist. New privacy laws passed in 2025 and 2026 draw a clear line. Raw gate data belongs to the individual. City operators may own anonymized data, anonymized force data, anonymized timing data, but never the identifiable gate signature. The technical fix is anonymization at the edge. The microchip in each tile processes raw sensor data locally and converts it immediately into a simple anonymous event. A person was here. Biometric details are discarded and never transmitted or stored. This preserves what cities need, crowd flow density while protecting individual privacy. Transparency is key. The public must understand what the tech is and what it does. Place clear signage where kinetic floors are installed. Signage should explain the floor captures wasted energy from footsteps to power local services like lights, chargers. This builds public trust and reframes the tech as collaboration, not surveillance. Another concern is unforeseen consequences. Could vibrations damage a historic building? Could a cybersecurity breach target the network? Mitigations include careful engineering adherence to standards, robust security protocols, modal analysis tests prevent vibration issues, end-to-end encryption certified security hardware, protect the network from intrusion. By anticipating risks and designing solutions from the start, cities can deploy kinetic tech responsibly, ensuring benefits, clean energy, smart data, do not come at the cost of safety or personal freedom.